The one puppy goes in with a 5, or some of the 5 go in with the 1.
They can both happen.
Yeah, but which is more likely?
5 into 1.
5 into 1, right? It's just more likely. And here's why. When there is crowding and bouncing around, normally, on average, the bouncing will bounce someone over to the less crowded side. Now, we know molecules all vibrate. It's called Brownian motion. And if we imagine 10 grams of some molecule vibrating over here, and only 1 gram of some molecule vibrating over here, we can imagine that if they could, just due to the random chance of vibrating and bumping into each other, they will mostly go over there. This movement from high concentration to low concentration is called diffusion. All right. So now, which side has more water on it? Side A or side B? Side A has more water. So the water is more crowded over here, right? So which way is the water going to go? That way. Over here. All right, water wants to go over here. I made it all wavy so you can say it's water. Salt wants to go over there. Let's call it sodium. Okay? So, that's why water is going from areas of low salt concentration to areas of high salt concentration, because the water is actually going from areas of high water concentration to low water concentration. If you have trouble remembering, things always go from high to low. Think of dropping a marker. It always goes from high to low, right? Same thing here. Things go from high concentration to low concentration. Boom. Okay. So some words. Diffusion is when any molecule goes from high to low concentration. Osmosis is when water goes from high to low concentration. Because water is so special, we have a special word for water diffusion, osmosis. Okay. Other important words. Tonic is Latin for strong. Hypo is Latin for less. Iso is Latin for same. And hyper is Latin for extra. So let's look at these two solutions here. Which solution would you say is stronger? The one that's more concentrated, right? So it is hypertonic to that one. This one is hypotonic to this one. And if I were to add some salt in here, well, now they are isotonic to each other. They're suddenly the same strength. The word hypotonic, isotonic, and hypertonic is a comparison word, like taller than, shorter than, right? Heavier than, lighter than. It is always a comparison, and you cannot use it in isolation. If I were to say the cell is hypertonic, it must mean it's hypertonic to its environment. If I say the environment is hypertonic, it must be hypertonic in comparison to the cell. Make sense? So let us all draw some cells, okay? Let us draw a cell that is hypertonic to its environment. Cell hypertonic to its environment. So now, in this situation, what would we expect to happen? The salt in the cell is going to want to go where?
Out.
Out. So the salt wants to go out here. Now this is a big glass of water and this is a very small cell. So will the cell ever be able to let enough salt leave to become isotonic with its environment? No. Environment is just too big. So where does the water want to go?
Water wants to go.
And the water is going to keep wanting to go in, and it's going to keep going in if it can, until what happens to the cell?
R.I.P. Pieces.
Rip, burst. Yeah. The formal word is lyse, aka kaboom. Okay. So, what if instead the environment was hypertonic to the cell? Where does the salt want to go?
Into the cell.
Into the cell. And where does the water want to go? Out of the cell. So what's going to happen to the cell? It's going to shrivel up. It's going to be very prune-like. Now, of course, if things were isotonic, would the salt move?
It might.
Well, yeah, because here's what happens. Things are always moving, right? But the thing is, if it's isotonic, then it moves in one direction with the same average frequency as it's going to move in the other direction, right? On average, there's no net movement. So, no net movement if we are, there you go. No net movement if we're in an isotonic situation. And so because there's no net movement, we call it equilibrium. Equilibrium when both things in both directions are equal. All right? So in an isotonic environment, we will see no swelling or shrinking of the cell, right? The cell will remain normal. Now, what if I were to put a cell wall around the cell? What if this became a plant cell? Would it still lyse? No, why not? As the cell starts swelling, the walls of the cell start pushing back. So, okay. If we think about all of the things that act on water, we would say that okay, so new vocabulary. We're doing this. We're skipping ahead to chapter 36.
What?
Trust me, you want to do this now, not later. It'll get confusing later.
What's
Okay.
36 about?
Water.
Oh,
We're just doing all the water at once.
okay.
Okay. So you don't have to go there yet. You're okay. But let's think when water moves around, there's a lot of things acting on it. For example, if I had a little syringe right here, right? And it had like water in it, and then it had that plunger, right? Okay. So we have our syringe, we have water in the syringe, we have a plunger. If we're pushing on the plunger, what's going to happen to the water?
Comes out.
Comes out. So clearly, creating a physical pressure on the water makes the water move. Okay. What if we were to pull on the plunger? Water would go in, right? Because we're creating a negative pull. We're creating a pull, right? Okay. So we will talk about that thing happening with that plunger as the pressure potential of water. So this trident shape is some sort of Greek letter, I don't know what it's called, but we use it to talk about water potential, the potential energy of water. Which way does water want to go? Right? Just like there is potential energy of, okay, if I'm holding the marker up here, where does the marker want to go?
Down.
It has a potential energy, right? So if there's water in the syringe, right, and I am pushing down on the plunger, but there's a cap, I'm still pushing down on the plunger, right? So there's a water potential. It wants to go somewhere, even if it can't because there's a cap, right? Okay, so here we're talking about the water potential due to pressure. If the water wants to leave, we would say it's a positive potential. If the water wants to come in, it's being pulled in, we would say it's a more negative potential. So I'm just going to give you guys a little table to help you memorize these things. So we have the pressure potential. If the water wants to come in versus come out. If it wants to come in, it's going to be negative and we're getting a pull. If it wants to come out, it's going to be positive and we're getting a push. Now we also have a water potential due to solutes. Take a look right here. The water potential due to solutes, when the cell is hypertonic, is pulling water into the cell, right? So the water wants to come in, and the solute potential is negative, and it's because we're really salty, and we're pulling it in. Okay? On the other hand, here, there is a push. The water is being pushed out of the cell. So we would say this potential is positive, we have a push, and because we're too dilute, we're not salty enough compared to our environment. And now, of course, the total potential of water is the pressure plus the solute potential. They gotta get added up together. And that happens when we have a cell wall because the cell wall creates pressure. Make sense to everybody? Cell walls can create pressure, so that's why we need to think about pressure as well as solute potential. So let's look at this right here. Because the inside is really salty, what will be the solute potential? Negative. It's going to pull us in, right? It's going to be some sort of negative number. I'll just give it a number. Negative 0.5. Because that's the number I gave it. Okay? There's ways of calculating it. I can't be bothered. So now water is starting to go in, right? So as the water goes in, the membrane is going to start pushing against that wall. So there is going to be a push, a positive pressure potential, right? And that pressure potential is going to keep increasing and increasing and increasing until it equals 0.5. Because at that point, the total potential would equal 0. How about the total potential of the water out here? So this is the total potential of the water in here, right? What about the total potential of the water out here? Well, let's see. It's got, let's say it's got no solutes. It's pure water. No solutes, pure water. That's going to be a solute potential of 0. And there's nothing pushing on that water, right? There's no plunger. So that's a pressure potential of 0. When the total potential of the environment equals the total potential of the cell, there is no net water movement. We are at equilibrium. But when there is a difference, right, before water went into the cell, when the pressure potential was 0, So the total potential was negative 0.5, yeah? Then there was a difference. The cell had a lower potential, and the water went from the higher potential to the lower potential, from the environment into the cell. Okay. Thumbs up if it makes total sense, you got this. Okay. Thumbs half mast if we're like moderately confused. And thumbs plunging downward if we have so many questions it's not even funny, we need help. Okay, cool. So there will be homework on this. Do the homework. Make sure you can do the homework. If you can do the homework, you know you've got this concept. Yeah? If you have troubles with the homework, ask me in class next week and we'll